thanks for tuning in. Let's take a little bit of time to kind of review our analogy that we've been using for circuits. So just in general, at the bottom of our post office document here, we've got some general key terms and colors for you guys to identify some prominent terms that we'll be using. So the first is the charge carriers, which you guys know could either be negatively charged or positively charged. Positive charge carriers would indicate when they flow the direction of conventional current, and negative charge carriers would flow then the opposite way for us in a circuit. The units of our charge carriers are coulombs. So coulombs are the unit that we use to measure how many charge carriers or how much charge we have. Underneath of that, you see current, represented by the variable I. Current is the rate of flow of the charge carriers. So you cannot use the terms charge and current interchangeably. Current measures how quickly the charges flow through the circuit. They are not the charges themselves. The unit for current is an ampere, represented by the letter A, and an ampere is 1 coulomb per second. So if you have a current of 5 amperes, that means every second 5 coulombs would pass the point at which you're measuring. Then we see resistance, R. Resistance is a hindrance to the flow of charge. So it's a hindrance to current. The units of resistance are ohms, and that is indicated or represented by the capital Greek letter omega. And finally, arguably one of the most important parts of our circuit, without which we would not have current, is the electrical potential difference, represented to us by delta V. Also, it is the change in electrical potential energy per charge between 2 points. So in a sense, you're looking at how much charge does the coulomb or does the charge carrier have at point A versus how much potential energy does that charge have at point B. And the difference between those amounts of energy per charge is the electrical potential difference. We measure that with the units volts, represented by the letter V. So let's go on back up to the top and talk about the analogy we've been using for a circuit. So we said that the post office functions like our power source or like our battery, over which there will be an electrical potential difference. So going back down to our color codes, we used purple. We said that there would be an electrical potential difference across the post office that would indicate the delta V of the whole circuit or the delta V across the battery. We said that the postman would represent the coulombs or the charge carriers, and that the packages that the postman carries would represent the electrical potential energy. So that means that the electrical potential energy per charge could be calculated using delta V, and we can actually find the electrical potential difference not just over the post office, but actually between any 2 points along the circuit. So the analogy was that the postmen who are already on this path, just as the electrons or the charges are already part of the circuit, the postmen start to move on the path as soon as the path has a post office connected to it, much in the same way that current will start to flow in the circuit as soon as we have a battery or a power source with an electrical potential difference across it that causes the current to flow. So electrical potential difference causes the current to flow, just like the pipe analogy we used in class, where we said if you have a pipe with some water in it and you hold it up horizontally to the parallel to the ground, and it's horizontally in your hands, then the water will not flow from one end of the pipe to the other until you tilt the pipe and one end of the pipe is higher than the other. And in that same way, unless there is a place of high electrical potential energy in your circuit and a place of very low electrical potential energy in your circuit, the electrons will not flow as a current. Okay, they will just continue to collide with one another and move in an arbitrary fashion. They will not flow as a current. So getting back to our analogy, the postman or the Coulombs leave the post office with a bag full of packages. The packages are the joules of energy. Now the postman will pass through houses on his path, and he must return back to the post office at the end of all of his route with a bag that is completely empty, meaning he has to get rid of all his joules of energy along this path. Now the postman is a fair postman if he sees two houses that are the same. So in this example on our screen, if house 1 and house 2 have the same resistance, then he will drop off half of his packages at the first house and half of his packages at the second house. So you can see here we've got the postman on the route leaving with 2 packages each. So each postman has 2 capital E's of energy, or 2 packages. The postman will drop off the first package at house number 1 and continue on the path with 1 package of energy left, and he'll drop off the second package at house 2, and he will leave house 2 with no energy left, and he'll return back to the post office with 0 packages or 0 joules of energy, and the process will start again. So this is where we made our conclusion that with 2 resistors in series, 2 identical resistors, 50% of the total electrical potential energy will be used by the first resistor, and 50% of it will be used by the second resistor. So if we have a 3-volt battery, meaning 3 joules of energy per coulomb of charge, then that's like each postman having 3 packages with him. And each postman would drop off 1.5 packages at each house, or each coulomb would drop off 1.5 joules of energy to each resistor. Now, using the ammeter, which measures current, we could have measured the current at any place along this path, and we would have seen that the current at any point on the path, whether it's between the post office and house 1, or between house 1 and house 2, etc., the current would be the same. The voltmeter, or the multimeter that we used in class, was to measure the potential difference across a resistor. So rather than being assembled in series, like the ammeter was, where it had to be part of the circuit, the voltmeter used the 2 probes to measure the potential difference across 2 different points in your circuit. So if you were to use the voltmeter to measure the potential difference across the first house, you would see that the reading would be negative 1.5 volts. And that's the same reading you would get if you measured the potential difference across the second house. So each coulomb is passing through the each coulomb is passing through the battery, picking up 3 joules of energy with it, and then dropping off 1.5 joules at the first house, which is why it's a negative reading, and then dropping off the remaining 1.5 joules at the second house. So each bulb in series burns only half as bright as the single bulb in the circuit. It's getting only half as much energy. Now that's a different situation than if you look at 2 bulbs or 2 houses arranged in parallel in which each postman or each coulomb chooses which path to go down. So for example, postman 1 might choose the first house and drop off all his packages at the first house, and then the postman who's right behind him might choose the second house and then go down that path and drop off all his packages at the second house. Postman 3 would go back to the first house, and postman 4 would go back to the second house, and so on and so forth. The same thing will happen with the coulomb. So the coulomb will pass through the post office and pick up 3 joules of energy again, and drop off the entire 3 joules at the house that they choose to pass through. And then the next postman will drop off the entire 3 joules at the other house that was not chosen by the first coulomb. So you can predict here that if you were to take a reading on the voltmeter of the potential difference across each of these houses, you would get a reading of negative 3 volts across each house, because each coulomb is losing a total of 3 joules of energy by passing through the resistor. And that's why each bulb set up in parallel, when there's two bulbs set up in parallel, they are just as bright as the bulb that is in series. So then we get this slightly trickier situation, which you guys saw in the lab, which involved two houses in series, where one house has a greater resistance than the other. And intuitively, you might think that the house with the greater resistance would get the least amount of energy. But remember, from the lab, we actually saw the opposite happening. The light bulb with the highest resistance was lit, right? Burned brightly. And then the house with lesser resistance actually didn't even light at all. And so in this case, when the two houses or the two resistors are in series, the resistor with the highest resistance will be the brightest. And that was because of our Ohm's law situation, where we said we use Ohm's law, delta V equals IR. And now I'm actually reading from the notes down here at the bottom. We use delta V equals IR to calculate the current that would exist in each part of this circuit. And so in this sense, the higher the total resistance of the circuit, the lower the current. So we use that to calculate the current in each branch of our circuit. Then we use that current calculation with the resistance from each house or each resistor to calculate the delta V across each resistor. So you guys actually saw that today in the 17C homework, which we'll go over, where you used the delta V equals IR to calculate the current of 0.8 amperes in the circuit. This is the circuit that had the toaster, the lamp, and the oven, or the iron. And then you use that 0.8 amperes multiplied by the individual resistance of each resistor to actually tell you the delta V across the resistor. So that's explained a little bit more in depth here. And if you'd like to slow this down, you can go back up and read the explanation. Or you can also revisit homework 17C, which includes that problem of the 10 ohm toaster, the 20 ohm iron or oven, and then the 120 ohm lamp with a 120 volt power supply. So go ahead and revisit 17C if you'd like to take a look at that. Thanks for tuning in, and definitely come in for office hours if you need any more clarification. Thanks, guys.